All right, everyone. In the last video, we talked about the basics of probability theory. It was very abstract, very high level. So in this video, I want to give an example in case this wasn't clear that will hopefully help make it clear. Now, of course, you can have very simple degenerate examples, like you can have the case of flipping a fair coin and you have two outcomes, heads and tails, but this is almost too basic to be useful. So the example that I want to give is, suppose you have a fair die. So as a result, you're going to have six outcomes. Yeah, six outcomes is right. 1, 2, 3, 4, 5, and 6. And if this is a fair die, then the probability that we get the event E1 through E6, so this could be any one of them, is equal to 1/6, any of these individual events, and these specific events being the outcome. So remember, an event can be a specific outcome, or an event can be some collection of possible outcomes. The outcomes themselves have to be, disjoint. You either get one or the other, but the event can be a collection. You can say I can have this event, or this event, or this outcome, this outcome, this outcome. In fact, events can even be combinations of other events. But remember, at the ground level, you have outcomes. So you have basically you have your sample space, and inside of it you have outcomes, and then you have events, which are eventually, they're always made out of outcomes, but of course by joining events together, you're just basically filtering through the different outcomes that you have. So to give an example, we can have different outcomes here, different events that are collections of outcomes. So we can have the event even, which would then be this here. And of course we could say the probability of E even equals, it's the probability of basically the events of getting any of the events in my collection or any of the outcomes in my event divided by, or the probabilities of each of these divided by the total number of events. In this case, particularly, we have the whole sample space, which the probability is 1, but this will come in handy later. So here we basically have 1, 6, 1, 6, and 1, 6. This is equal to 1/2. That's what we have. So basically finding the probability of an event is just adding together or summing together or integrating together the probabilities of the outcomes contained within the event, which is pretty useful. We can also have the event E greater than or equal to 3. So the probability of E being greater than or equal to 3 is equal to, and if I show you what this looks like, it's going to be these 4 numbers. This is equal to 1, 2, 3, 4. So 4/6, or of course 2/3. And we can even have another event, and I'll explain why I did this before. E greater than or equal to 4, which is the probability, and we can have, of course, probability, the event of being greater than or equal to 4. And this is this particular event, so this sort of L-shaped block here. And this has a probability of 1, 2, 3. 3/3 times 1/6, or 1/2. So now we can actually look at doing some interesting things with these. For instance, we can talk about intersections of events. So we can say, for instance, I want to find the event E even greater than or equal to 4. Well, what this is going to be is, what I'm looking for is the probability of the event E being even intersected with the event E being greater than or equal to 4. So we need to find all of the places where the green, it's contained in the green, and it's also contained in the red. So this is like the Christmas event. And here what we're going to do is we look here and we see that we have 4 and 6. These are our 2 options. So the probability here, the event, so maybe what I should say first is the event E even intersected with E greater than or equal to 4 is the set 4 and 6, because we're taking the set intersection of 2, 4, and 6 with the set 4, 5, and 6, and the intersection of those two is 4 and 6, and then we just need to find the probability of those particular events that are contained within this the set intersection here, and this is simply equal to 2/6, or 1/3. The other thing we can do is do an or a union operator. So we can say the probability that my number is even, or the event that the number that I roll is greater than or equal to 4. And once again, for set union, you just find the elements contained within both sets. Now, if we remember before, if we want to calculate this probability, the easiest thing to do is calculate the probability of the first event, add the probability of the second event, and then subtract the intersection, because once again, you're double counting for both of them. So in this case, we have the even numbers, which are 2, 4, and 6, and then the event greater than or equal to 4, which is 4, 5, and 6. But notice how we've double counted 4 and 6. So if we want to find the possibility of doing this, the numbers we're trying to find is the probability of getting 2, 4, 5, and 6, but we don't want to double count for the ones that are included with both. So this is, of course, equal to the probability that my number is even plus the probability that my number is greater than or equal to 4 minus the probability of them both happening so we don't double count. Intersection, the event being greater than or equal to 4. And of course we can substitute these in. This is equal to 1/2 plus this is 1/2. And then we're basically going to minus what we got before, 1/3. So we have, getting a common denominator, you have 3, 6 plus 3, 6 minus 2, 6. So this equals 4, 6, or 2/3. And this makes sense, right? When we look here, we look at basically what's included in either red or green or both. You get 2, 4, 5, and 6. And that's 4 out of the 6 possibilities. And we're able to do this because they have equal probability. If they didn't, you'd have to kind of weight these based on their probabilities, and we can look at that in another case. So now what I want to do is look at 2 of these conditional probability versions of this. So what I want to do is say, what's the probability that my number is even, the event E even, conditioned on the event E greater than or equal to 3. So this is going to be the first one that I do. And what we're going to do is we're basically going to take a look at this, and by staring at this, we can say, well, the event that it's greater than or equal to 3 is me restricting my sample space. It's me defining a new sample space where we basically only have the numbers 3, 4, or sorry, this would be because we're conditioning on greater than or equal to 3. Oh yeah, that's right. We have greater than or equal to 3, we're going to have 3, 4, 5, and 6. So because we're conditioning on this, we're kind of zooming into this particular thing, and now we need to re-index our probability function so that we have a valid sample space. So what this is going to mean is the probability of any outcome, just going to say W, because this is fair, is not 1/6, now it's 1/4. So we've had to change these so that we obey the axiom of probability that the probability of our new sample space is 1. Now, looking at this and looking at what we have here, the probability that it's even is simply, if we just, go back to red, is these 2 out of the 4. So what we have here, of course, is this probability is 2/4, or 1/2. And because the probability, E even, conditioned on E greater than or equal to 3, is equal to the probability of E even, we say that these 2 events are statistically independent. Even we write it like this. This is the symbol for orthogonality. Now we'll talk later about how orthogonality in a linear algebra sense or geometric sense relates to probability distributions and these sorts of things. But right now, or events, right now, basically we can say that the event even is independent of the event of rolling a number greater than or equal to 3. Once again, this is because what we've done here is used this particular definition of independence. So there we go. Now, if we look at the probability that E is even conditioned on the event e being greater than or equal to 4, what we can then do is look here at our original sample space. What we're going to start with, of course, is the boot that we see before. And we have 4, 5, and 6. And now the probability that I have an even number is 2 out of my 3 possible outcomes. So this equals 2/3. Notice how this does not equal the 1/2 we had before. So the event of getting an even number is not independent of getting a number greater than or equal to 4. In other words, getting a number greater than or equal to 4 actually tells me some additional information or helps me reduce the uncertainty in my calculation in some particular way. It gives me additional knowledge about things. So that is where this comes up. And of course, what Bayes' rule, where Bayes' rule comes in, is what we do is we take the probability of any individual event and we divide by the probability of the event we conditioned on. So in this case, remember, we divided this, we took our thing and we divided it by the denominator. So in our greater than or equal to 3 case, this is where this 4 comes from. This is right out of Bayes' rule, where we simply divide by the probability of A. And over here, we did the same thing. We have our denominator 3, and this came out because we had 3 possible outcomes, and the ones that we care about are the 2 of those particular 3. So this is the relationship between sets. So anyway, hope you found this helpful. Hope you learned something. In the next video, we will be talking about random variables.